Thank you for joining me on this adventure. Your presence means the world to me. Welcome, friends, to our video dedicated to Bernoulli's principle. Let's dive right in and uncover its wonders. Bernoulli's principle is a key concept in fluid dynamics that relates pressure, speed, and height. For example, for a fluid flowing horizontally, Bernoulli's principle states that an increase in the speed occurs simultaneously with a decrease in pressure. The principle is named after the Swiss mathematician and physicist Daniel Bernoulli, who published it in his book Hydrodynamica in 1738. Although Bernoulli deduced that pressure decreases when the flow speed increases, it was Leonhard Euler in 1752 who derived Bernoulli's equation in its usual form. Bernoulli's principle can be derived from the principle of conservation of energy. This states that, in a steady flow, the sum of all forms of energy in a fluid is the same at all points that are free of viscous forces. This requires that the sum of kinetic energy, potential energy, and internal energy remains constant. Thus, an increase in the speed of the fluid implying an increase in its kinetic energy occurs with a simultaneous decrease in the sum of its potential energy, including the static pressure and internal energy. If the fluid is flowing out of a reservoir, the sum of all forms of energy is the same because in a reservoir the energy per unit volume, the sum of pressure and gravitational potential, is the same everywhere. Bernoulli's principle can also be derived directly from Isaac Newton's second law of motion. When a fluid is flowing horizontally from a region of high pressure to a region of low pressure, there is more pressure from behind than in front. This gives a net force on the volume, accelerating it along the streamline. Fluid particles are subject only to pressure and their own weight. If a fluid is flowing horizontally and along a section of a streamline, where the speed increases, it can only be because the fluid on that section has moved from a region of higher pressure to a region of lower pressure, and if its speed decreases, it can only be because it has moved from a region of lower pressure to a region of higher pressure. Consequently, within a fluid flowing horizontally, the highest speed occurs where the pressure is lowest, and the lowest speed occurs where the pressure is highest. Bernoulli's principle is only applicable for isentropic flows, when the effects of irreversible processes like turbulence and non-adiabatic processes, e.g. thermal radiation, are small and can be neglected. However, the principle can be applied to various types of flow within these bounds, resulting in various forms of Bernoulli's equation. The simple form of Bernoulli's equation is valid for incompressible flows, e.g. most liquid flows and gases moving at low Mach number. More advanced forms may be applied to compressible flows at higher Mach numbers. As we progress through this video, let's now turn our gaze towards incompressible flow equation. In most flows of liquids and of gases at low Mach number, the density of a fluid parcel can be considered to be constant, regardless of pressure variations in the flow. Therefore, the fluid can be considered to be incompressible, and these flows are called incompressible flows. Bernoulli performed his experiments on liquids, so his equation in its original form is valid only for incompressible flow. A common form of Bernoulli's equation is: V is the fluid flow speed at a point, g is the acceleration due to gravity, z is the elevation of the point above a reference plane, with the positive z direction pointing upwards, so in the direction opposite to the gravitational acceleration. P is the static pressure at the chosen point, and is the density of the fluid at all points in the fluid. Bernoulli's equation and the Bernoulli constant are applicable throughout any region of flow where the energy per unit mass is uniform. Because the energy per unit mass of liquid in a well-mixed reservoir is uniform throughout, Bernoulli's equation can be used to analyze the fluid flow everywhere in that reservoir, including pipes or flow fields that the reservoir feeds, except where viscous forces dominate and erode the energy per unit mass. The following assumptions must be met for this Bernoulli equation to apply. Flow must be steady, that is, the flow parameters velocity, density, etc. At any point cannot change with time. The flow must be incompressible even though pressure varies. The density must remain constant along a streamline. Friction by viscous forces must be negligible. For conservative force fields not limited to the gravitational field, Bernoulli's equation can be generalized as R frac psi R frac per ho a text instant where is the force potential at the point considered. For example, for the Earth's gravity, by multiplying with the fluid density, equation can be rewritten as a frac of rho gz plus p a text instant or q is constant where is dynamic pressure is the piezometric head or hydraulic head the sum of the elevation and the pressure head and is the stagnation pressure the sum of the static pressure and dynamic pressure. The constant in the Bernoulli equation can be normalized. A common approach is in terms of total head or energy head. H equals E L frac per rho G L frac Vog equal H L frac Vog. The above equations suggest there is a flow speed at which pressure is zero, and at even higher speeds the pressure is negative. Most often, gases and liquids are not capable of negative absolute pressure, or even zero pressure, so clearly Bernoulli's equation ceases to be valid before zero pressure is reached. In liquids, when the pressure becomes too low, cavitation occurs. The above equations use a linear relationship between flow speed squared and pressure. At higher flow speeds in gases, or for sound waves in liquid, the changes in mass density become significant so that the assumption of constant density is invalid. Brace yourselves for the next chapter, where we'll be dissecting simplified form. In many applications of Bernoulli's equation, the change in a term is so small compared with the other terms that it can be ignored. For example, in the case of aircraft in flight, the change in height is so small the term can be omitted. This allows the above equation to be presented in the following simplified form. PQ where is called total pressure and is dynamic pressure. Many authors refer to the pressure as static pressure to distinguish it from total pressure and dynamic pressure. In aerodynamics, L.J. Clancy writes, to distinguish it from the total and dynamic pressures, the actual pressure of the fluid, which is associated not with its motion but with its state, is often referred to as the static pressure, but where the term pressure alone is used it refers to this static pressure. The simplified form of Bernoulli's equation can be summarized in the following memorable word equation. Every point in a steadily flowing fluid, regardless of the fluid speed at that point, has its own unique static pressure and dynamic pressure. Their sum is defined to be the total pressure. The significance of Bernoulli's principle can now be summarized as total pressure is constant in any region free of viscous forces. If the fluid flow is brought to rest at some point, this point is called a stagnation point, and at this point the static pressure is equal to the stagnation pressure. If the fluid flow is irrotational, the total pressure is uniform, and Bernoulli's principle can be summarized as total pressure is constant everywhere in the fluid flow. It is reasonable to assume that irrotational flow exists in any situation where a large body of fluid is flowing past a solid body. Examples are aircraft in flight and ships moving in open bodies of water. However, Bernoulli's principle importantly does not apply in the boundary layer such as in flow through long pipes. As we enter this new chapter, let's navigate the complexities of unsteady potential flow and unravel its multifaceted nature. The Bernoulli equation for unsteady potential flow is used in the theory of ocean surface waves and acoustics. For an irrotational flow, the flow velocity can be described as the gradient of a velocity potential. In that case, and for a constant density, the momentum equations of the Euler equations can be integrated to frac partial varphi partial t frac val frac per ho plus x equal ft, which is a Bernoulli equation valid also for unsteady time-dependent flows. Here denotes the partial derivative of the velocity potential with respect to time, and is the flow speed. The function depends only on time and not on position in the fluid. As a result, the Bernoulli equation at some moment applies in the whole fluid domain. This is also true for the special case of a steady irrotational flow, in which case and are constants, so equation can be applied in every point of the fluid domain. Further can be made equal to zero by incorporating it into the velocity potential using the transformation tft, resulting in r frac partial phi partial t frac val frac per ho plus x equal. Note that the relation of the potential to the flow velocity is unaffected by this transformation. The Bernoulli equation for unsteady potential flow also appears to play a central role in Luke's variational principle, a variational description of free surface flows using the Lagrangian mechanics. In this chapter, we'll be shedding light on compressible flow equation and its role in shaping our understanding. Bernoulli developed his principle from observations on liquids, and Bernoulli's equation is valid for ideal fluids, those that are inviscid, incompressible and subjected only to conservative forces. It is sometimes valid for the flow of gases as well, provided that there is no transfer of kinetic or potential energy from the gas flow to the compression or expansion of the gas. If both the gas pressure and volume change simultaneously, then work will be done on or by the gas. In this case, Bernoulli's equation in its incompressible flow form cannot be assumed to be valid. However, if the gas process is entirely isobaric or isochoric, then no work is done on or by the gas, so the simple energy balance is not upset. According to the gas law, an isobaric or isochoric process is ordinarily the only way to ensure constant density in a gas. Also, the gas density will be proportional to the ratio of pressure and absolute temperature. However, this ratio will vary upon compression or expansion, no matter what non-zero quantity of heat is added or removed. The only exception is if the net heat transfer is zero, as in a complete thermodynamic cycle or in an individual isentropic frictionless adiabatic process, and even then this reversible process must be reversed to restore the gas to the original pressure and specific volume, and thus density. Only then is the original, unmodified Bernoulli equation applicable. In this case, the equation can be used if the flow speed of the gas is sufficiently below the speed of sound, such that the variation in density of the gas due to this effect along each streamline can be ignored. Adiabatic flow at less than Mach 0.3 is generally considered to be slow enough. It is possible to use the fundamental principles of physics to develop similar equations applicable to compressible fluids. There are numerous equations, each tailored for a particular application, but all are analogous to Bernoulli's equation and all rely on nothing more than the fundamental principles of physics such as Newton's laws of motion or the first law of thermodynamics. Get ready for a captivating exploration as we unravel the layers of compressible flow in fluid dynamics and their profound significance. For a compressible fluid, with a barotropic equation of state, and under the action of conservative forces, a frac event p a frac a mathematical tilde per whole of tau tilde per right side a text constant along a streamline whereas the pressure is the density and indicates that it is a function of pressure is the flow speed is the potential associated with the conservative force field, often the gravitational potential. In engineering situations, elevations are generally small compared to the size of the Earth, and the time scales of fluid flow are small enough to consider the equation of state as adiabatic. In this case, the above equation for an ideal gas becomes a frac if there's a left frac a gamma gamma a right frac I per ho a text constant along a streamline where, in addition to the terms listed above is the ratio of the specific heats of the fluid is the acceleration due to gravity is the elevation of the point above a reference plane. In many applications of compressible flow, changes in elevation are negligible compared to the other terms, so the term can be omitted. A very useful form of the equation is then a frac of a left frac a gamma gamma a right frac I per ho a left frac a gamma gamma a right frac p arrow. Whereas the total pressure is the total density. Our focus now turns to compressible flow in thermodynamics, an important aspect of our discussion. The most general form of the equation, suitable for use in thermodynamics in case of quasi-steady flow, is a frac psi plus W a text constant. Here is the enthalpy per unit mass, also known as specific enthalpy, which is also often written as not to be confused with head or height. Note that W e a frac per ho a left frac gamma gamma a frac per right where is the thermodynamic energy per unit mass, also known as the specific internal energy. So, for constant internal energy E the equation reduces to the incompressible flow form. The constant on the right-hand side is often called the Bernoulli constant and denoted. For steady inviscid adiabatic flow with no additional sources or sinks of energy, is constant along any given streamline. More generally, when may vary along streamlines, it still proves a useful parameter related to the head of the fluid, see below. When the change in can be ignored, a very useful form of this equation is R frac plus W equal W, where is total enthalpy. For a calorically perfect gas such as an ideal gas, the enthalpy is directly proportional to the temperature, and this leads to the concept of the total or stagnation temperature. When shock waves are present, in a reference frame in which the shock is stationary and the flow is steady, many of the parameters in the Bernoulli equation suffer abrupt changes in passing through the shock. The Bernoulli parameter remains unaffected. An exception to this rule is radiated shocks, which violate the assumptions leading to the Bernoulli equation, namely the lack of additional sinks or sources of energy. Brace yourself for a deep dive into unsteady potential flow as we explore its impact and relevance in our evolving narrative. For a compressible fluid, with a barotropic equation of state, the unsteady momentum conservation equation R frac partial vig for partial t left of if det nabla right vig equal evic if nabla per ho. With the irrotational assumption, namely, the flow velocity can be described as the gradient of a velocity potential. The unsteady momentum conservation equation becomes R frac partial nabla phi partial t nabla frac nabla fictit nabla phi right equal nabla t nabla int p up frac tilde per ho tilde, which leads to R frac partial phi partial t R frac nabla fictit nabla phi psi int p up frac tilde per ho tilde, a text constant. In this case, the above equation for isentropic flow becomes R frac partial phi partial t R frac nabla fictit nabla phi psi R frac gamma gamma R frac per ho, a text instant. In this section, we'll be deep diving into derivations, unraveling its complexities and uncovering valuable insights. Our mathematics are left frac the right. With density constant, the equation of motion can be written as R frac mathematics left ho frac plus per right by integrating with respect to R frac per ho c, where is a constant, sometimes referred to as the Bernoulli constant. It is not a universal constant, but rather a constant of a particular fluid system. The deduction is, where the speed is large, pressure is low, and vice versa. In the above derivation, no external work energy principle is invoked. Rather, Bernoulli's principle was derived by a simple manipulation of Newton's second law. Derivation by using conservation of energy. Another way to derive Bernoulli's principle for an incompressible flow is by applying conservation of energy, in the form of the work-energy theorem, stating that therefore, the system consists of the volume of fluid, initially between the cross-sections and, in the time interval, fluid elements initially at the inflow cross-section move over a distance, while at the outflow cross-section the fluid moves away from cross-section over a distance. The displaced fluid volumes at the inflow and outflow are respectively and. The associated displaced fluid masses are when is the fluid's mass density equal to density times volume, so and. I mass conservation, these two masses displaced in the time interval have to be equal, and this displaced mass is denoted by a beginner linear ho 1 s1 rho 1 v a delta t delta mer ho 2 s2 rho 2 v a delta t delta my. The work done by the forces consists of two parts: the work done by the pressure acting on the areas and W a text depressor SF a text depressor S2 P1 a 1 S1 P2 a 2 S2 deltum frac a rho deltum frac a rho. The work done by gravity, the gravitational potential energy in the volume is lost, and at the outflow in the volume is gained. So, the change in gravitational potential energy in the time interval is hot gravity zungs. Now, the work by the force of gravity is opposite to the change in potential energy. While the force of gravity is in the negative direction, the work gravity force times change in elevation will be negative for a positive elevation change, while the corresponding potential energy change is positive. So, W gravity pot gravity zungs. and therefore the total work done in this time interval is W pressure W gravity. The increase in kinetic energy is delta E at extin for delta M, V at for delta M, V. Putting these together, the work kinetic energy theorem gives deltum frac rho deltum frac rho delta M, Gz1 delta M, Gz2 for delta M, V at for delta M, V or for delta M, V delta M, Gz1 deltum frac rho for delta M, V delta M, Gz2 deltum frac rho. After dividing by the mass, the result is frac Vgz1 frac rho frac Vgz2 frac rho, or, as stated in the first paragraph, further division by produces the following equation. Note that each term can be described in the length dimensions such as meters. This is the head equation derived from Bernoulli's principle. The middle term represents the potential energy of the fluid due to its elevation with respect to a reference plane. Now is called the elevation head and given the designation. A free-falling mass from an elevation in a vacuum will reach a speed v certs when arriving at elevation, or when rearranged as head, hv r frac g. The term is called the velocity head, expressed as a length measurement. It represents the internal energy of the fluid due to its motion. The hydrostatic pressure P is defined as ppg, with some reference pressure, or when rearranged as head, psi r frac rho g. The term is also called the pressure head, expressed as a length measurement. It represents the internal energy of the fluid due to the pressure exerted on the container. The head due to the flow speed and the head due to static pressure combined with the elevation above a reference plane, a simple relationship useful for incompressible fluids using the velocity head, elevation head, and pressure head is obtained. If E1 is multiplied by the density of the fluid, an equation with 3 pressure terms is obtained. Note that the pressure of the system is constant in this form of the Bernoulli equation. If the static pressure of the system, the third term increases, and if the pressure due to elevation, the middle term, is constant, then the dynamic pressure, the first term, must have decreased. In other words, if the speed of a fluid decreases and it is not due to an elevation difference, it must be due to an increase in the static pressure that is resisting the flow. All 3 equations are merely simplified versions of an energy balance on a system. Now, let's dig deeper into applications and unveil the hidden treasures it holds within. In modern everyday life, there are many observations that can be successfully explained by application of Bernoulli's principle, even though no real fluid is entirely inviscid, and a small viscosity often has a large effect on the flow. Bernoulli's principle can be used to calculate the lift force on an airfoil, if the behavior of the fluid flow in the vicinity of the foil is known. For example, if the air flowing past the top surface of an aircraft wing is moving faster than the air flowing past the bottom surface, then Bernoulli's principle implies that the pressure on the surfaces of the wing will be lower above than below. This pressure difference results in an upwards lifting force. Whenever the distribution of speed past the top and bottom surfaces of a wing is known, the lift forces can be calculated to a good approximation using Bernoulli's equations. The resultant force is determined by integrating the surface pressure distribution over the surface area of the airfoil, which were established by Bernoulli over a century before the first man-made wings were used for the purpose of flight. The basis of a carburetor used in many reciprocating engines is a throat in the airflow to create a region of low pressure to draw fuel into the carburetor and mix it thoroughly with the incoming air. The low pressure in the throat can be explained by Bernoulli's principle, where air in the throat is moving at its fastest speed and therefore it is at its lowest pressure. The carburetor may or may not use the difference between the 2 static pressures which result from the Venturi effect on the airflow in order to force the fuel to flow, and as a basis a carburetor may use the difference in pressure between the throat and local air pressure in the float bowl, or between the throat and a pitot tube at the air entry, an injector on a steam locomotive or a static boiler. The pitot tube and static port on an aircraft are used to determine the airspeed of the aircraft. These 2 devices are connected to the airspeed indicator, which determines the dynamic pressure of the airflow past the aircraft. Bernoulli's principle is used to calibrate the airspeed indicator so that it displays the indicated airspeed appropriate to the dynamic pressure. A de Laval nozzle utilizes Bernoulli's principle to create a force by turning pressure energy generated by the combustion of propellants into velocity. This then generates thrust by way of Newton's third law of motion. The flow speed of a fluid can be measured using a device such as a venturimeter or an orifice plate, which can be placed into a pipeline to reduce the diameter of the flow. For a horizontal device, the continuity equation shows that for an incompressible fluid, the reduction in diameter will cause an increase in the fluid flow speed. Subsequently, Bernoulli's principle then shows that there must be a decrease in the pressure in the reduced diameter region. This phenomenon is known as the Venturi effect. The maximum possible drain rate for a tank with a hole or tap at the base can be calculated directly from Bernoulli's equation and is found to be proportional to the square root of the height of the fluid in the tank. This is Torricelli's law, which is compatible with Bernoulli's principle. Increased viscosity lowers this drain rate. This is reflected in the discharge coefficient, which is a function of the Reynolds number, and the shape of the orifice. Bernoulli grip relies on this principle to create a non-contact adhesive force between the surface and the gripper. During a cricket match, bowlers continually polish one side of the ball. After some time, one side is quite rough and the other is still smooth. Hence, when the ball is bowled and passes through air, the speed on one side of the ball is faster than on the other, and this results in a pressure difference between the sides. This leads to the ball rotating, swinging while traveling through the air, giving advantage to the bowlers. Get ready for a captivating exploration as we unravel the layers of airfoil lift and their profound significance. One of the most common erroneous explanations of aerodynamic lift asserts that the air must traverse the upper and lower surfaces of a wing in the same amount of time, implying that since the upper surface presents a longer path, the air must be moving over the top of the wing faster than over the bottom. Bernoulli's principle is then cited to conclude that the pressure on top of the wing must be lower than on the bottom. Equal transit time applies to the flow around a body generating no lift, but there is no physical principle that requires equal transit time in cases of bodies generating lift. In fact, theory predicts and experiments confirm that the air traverses the top surface of a body experiencing lift in a shorter time than it traverses the bottom surface. The explanation based on equal transit time is false. While the equal time explanation is false, it is not the Bernoulli principle that is false, because this principle is well established. Bernoulli's equation is used correctly in common mathematical treatments of aerodynamic lift. As we enter this new phase, let's navigate the complexities of common classroom demonstrations and discover its practical applications. There are several common classroom demonstrations that are sometimes incorrectly explained using Bernoulli's principle. One involves holding a piece of paper horizontally so that it droops downward and then blowing over the top of it. As the demonstrator blows over the paper rises. It is then asserted that this is because faster moving air has lower pressure. One problem with this explanation can be seen by blowing along the bottom of the paper. If the deflection was caused by faster moving air, then the paper should deflect downward, but the paper deflects upward regardless of whether the faster moving air is on the top or the bottom. Another problem is that when the air leaves the demonstrator's mouth, it has the same pressure as the surrounding air. The air does not have lower pressure just because it is moving. In the demonstration, the static pressure of the air leaving the demonstrator's mouth is equal to the pressure of the surrounding air. A third problem is that it is false to make a connection between the flow on the two sides of the paper using Bernoulli's equation, since the air above and below are different flow fields and Bernoulli's principle only applies within a flow field. As the wording of the principle can change its implications, stating the principle correctly is important. What Bernoulli's principle actually says is that within a flow of constant energy, when fluid flows through a region of lower pressure, it speeds up and vice versa. Thus, Bernoulli's principle concerns itself with changes in speed and changes in pressure within a flow field. It cannot be used to compare different flow fields. A correct explanation of why the paper rises would observe that the plume follows the curve of the paper and that a curved streamline will develop a pressure gradient perpendicular to the direction of flow, with the lower pressure on the inside of the curve. Bernoulli's principle predicts that the decrease in pressure is associated with an increase in speed. In other words, as the air passes over the paper, it speeds up and moves faster than it was moving when it left the demonstrator's mouth. But this is not apparent from the demonstration. Other common classroom demonstrations, such as blowing between two suspended spheres, inflating a large bag, or suspending a ball in an airstream, are sometimes explained in a similarly misleading manner by saying faster moving air has lower pressure. Leave a comment below and let me know what you thought of this video.